So I'm going to talk about a sodium channel that doesn't get a lot of airplay amongst all the other sodium channels which have been explored as potential therapeutic targets. Mainly for the primary reason is it's been a very challenging channel to actually target because it took years to actually form a recombinant version of this channel, express it recombinantly. So I'm going to basically give you a little rationale for why 1,9 is a potentially good pain target. I'm going to give you some data about the overcoming the challenges of actually being able to do drug discovery about it, and then some of the remaining challenges. So as Mark showed yesterday, there are actually 9 NAV channels in mammals. I'm not going to go into the first 6 of those, but the last 3, the ones in green, the ones in green here, they're all relatively selectively expressed in sensory neurons, 1,7, 1,8, and 1,9. 1,7 you heard about yesterday, 1,8 we're not going to talk about, but it has been a target of interest for the development of pain therapeutics. But I'm going to talk about this one. Now, this channel has been shown for a long time. It's been known, it was cloned in 1999, I believe, from the Waxman lab. And they've done a lot of work in terms of looking at the expression and how it interacts with proteins in DRGs. But one of the challenges was, could we actually use it as a drug discovery target? Could we express it and characterize it a little bit more? So it's certainly in peripheral nerves which are involved in pain. So, and this is again work from the Waxman lab, showing that if you look at the afferents, the actual kind of DRGs, and actually the dorsal horn of the spinal cord where these come into the spinal cord, NAV 1.9 is there. So it's clearly kind of in the right place. Now, when you look at this current, and again, I'm not sure how many people in the audience are familiar with sodium current, or at least certainly NAV 1.9, but it doesn't look like your typical sodium current, which is essentially a sort of fast inactivating current like this NAV 1.7, again, the channel that you heard about yesterday. And even the slower one, 1.8, is still fast relative to NAV 1.9. You get this very slow activation, very slow inactivation. And if you look at the actual voltage dependence of activation, it's very hyperpolarized. So it activates at very negative potentials. And that's probably plays a role in determining what its role is. So if you actually look at the voltage dependence of NAV 1.9, which is this one in red, and you actually look at the voltage dependence of inactivation of this channel, you actually see that they actually overlap. And you end up with this pink area with this window current, where you've essentially got a sustained entry of sodium and essentially a depolarizing force around in a range that would cover the resting membrane potential of neurons. And so they actually act as a kind of probably a controller of resting membrane potential and thereby threshold for action potential firing. And so that's essentially shown here. So if you were just to do a cartoon figure of a sensory action potential, 1,9 probably plays a role in controlling the resting membrane potential and the rate at which potentially could get to the threshold. 1,7 plays a defining role in threshold, and then 1,8 probably is the primary thing that's involved in the upstroke of the action potential. Now, it's been known for a while through knockout studies that actually NAV 1.9 plays a role in pain transmission. Not all pain transmission. It seems to be that it's involved in inflammatory pain conditions primarily. It's been shown that if you put on inflammatory soup, you can get an upregulation of this channel. If you knock it out, you can actually affect both mechanical allodynia and thermal hypersensitivity of pathways in a mouse, and so you can see those in various in vivo models of being suppressed. But for neuropathic pain in mouse, it was not obvious that it was having a role. So it's been considered for a while to be essentially an inflammatory target, a primary pain target. Now, in 2014, a little bit more work was actually focused from David Bullman's work looking at actually NAV 1.9 in the gastrointestinal tract. It's actually expressed in enteric neurons and seems to be involved both in the sensory afferents and may even be motility of the gastrointestinal tract. They showed very nicely using knockout studies that if you actually don't have NAV 1.9, the gut does not respond to things like inflammatory mediators like supernatants from humans suffering from Crohn's disease or kind of inflammatory bowel disease. So again, it's a nice piece of data to suggest that that channel is involved in certainly maybe visceral sensory sensations and maybe visceral pain. There was a recent study, I think at the end of last year, from John Wood's group that did actually try to suggest that there may be a role in neuropathic pain. They were looking at actually orofacial pain in mice, a knockout model of trigeminal neuralgia. Again, heat and mechanical sensations were affected in those models. So maybe there's a neuropathic pain role as well. And finally, even to, this year, there's been some work on looking at actually just the fibers, C fibers themselves, looking at the conduction properties and showing that in knockout mice, they could greatly affect the C fibers specifically. Certainly their heat and mechanosensitive fibers are affected, and they're actually reduced as a population. So clearly some nice evidence from knockout studies that 1.9 is involved. But clearly, I think the real piece of evidence that really got everybody excited was this one. And this is a study by Leopold in 2013, where they actually characterized a NAV1.9 mutation, L811P, which is a mutation on the bottom of the S6 in domain 2, where they showed that there were patients which had no sensitivity to pain. So like Mark told you yesterday about 1.7, these people do not sense pain. And this results in all sorts of nasty things, like they get multiple painless fractures, they do a lot of self-inflicted injuries, and actually they all have chronic diarrhea, which obviously goes along with that thing I was telling you about the role of NAV1.9 probably in the gastrointestinal tract. That same mutation was found by another group, Jeff Woods, here in actually Cambridge, similar sort of properties. And when actually Leopold looked at that mutation, when it expressed it in a recombinant system, he basically showed that that mutation caused a shift in the voltage dependence of activation. It made it easier to open at voltages which are around the resting membrane potential. So essentially you were adding a depolarizing force. There was not much going on in the way of inactivation, but clearly there was an enhancement, although I'm not sure that's relative. It's the shift that's probably the more important, because you don't know whether in a recombinant system whether the increased expression is just an artifact. But that was interesting. And then, is that a common feature? Well, actually, another mutation was found and was published on last year, and that's this one, this L1302F, which is actually on the bottom of S6 of domain 3. So it's in the same region, but on a different homology domain. And again, these were completely insensitive to pain. They actually maintained, at least this is a single family, mother and son and daughter. They had, sometimes they still had itch, but they all suffered from painless fractures and self-inflicted injuries, and they also had chronic diarrhea. So again, the common sort of phenotype. This publication actually published all this data, but they didn't publish any functional stuff. So they assumed it was a gain of function, but they didn't actually provide any data. Interestingly, we have worked on that same mutation. It turns out it's been found I think 3 or 4 separate times by different investigators, so it is actually a common mutation from a rare disease. And so we actually made that cell line where we actually made the mutation, and we found, like P8011, the Leopold mutation, we got a big shift, 30 millivolt shift in the voltage dependence of activation. And if you actually look at ultimately what that did, there was very little shift in inactivation. We found it actually shallowed that, and actually you might bring that back later on what that might be due to. But clearly what you see is this window current gets very, very large. So the depolarizing currents available to actually control membrane potential is that much larger, and maybe actually therefore controlling the process where actually the reason why you're not getting it's actually a loss, it feels like it's a loss of function in terms of actually pain, but it's a gain of function of the channel, is that you may depolarize the cell to a place where you maybe shut down other sodium channels and their ability to fire. Although there's actually some interesting kind of correlates to that. So here are these 2 mutations I've already showed you, the ones on D2 and D3. It turns out actually yet another one's just been found. It was published on a couple of months ago, which is on the bottom of S6 in domain 1. So there seems to be a common feature here in terms of the presence of these mutations and causing insensitivity pain. Now, a whole bunch of other mutations have been found. They're also gain of function, but unlike losing the sensation of pain, they all cause an increase in pain. So basically, there's been small fiber neuropathy mutations found. There's been familiar episodic pain mutations found in NAV1.9, and there's even been idiopathic erythromelalgia mutations found. All of those latter ones cause an increase in pain sensation, yet they gain in function. So why is that? How can you actually have both gain of function causing loss of pain and gain of pain? It turns out all of these other ones that cause the gain of pain, they cause a much smaller shift in the voltage dependence of activation than you see with the ones which cause the loss of pain. And there's been an argument that, and it's still controversial how that then leads to the different modalities. Some people say it's actually a depolarization that causes a shutdown of other channels. There may even be an effect on NaV 1.9 itself. I like this study from Leopold, where they actually compared a gain of function mutation that caused increase in pain versus their original loss of pain. And they just looked, and this happens to be the mutation they're showing here, is actually a cold sensitivity, that you change the temperature and suddenly the activation start firing rapidly, and so that's correlated with pain. If you look at the shift in the voltage dependence of activation, it's here, clearly not as much as with the 811P. But when they actually looked at sustained firing, you look at 1.9 in a wild type, and then you compare it to kind of this kind of gain of function positive cold sensitive mutation. You see you go from this firing rate to this, and it's sustained. It keeps going and going and going as long as you allow it to go. But when you looked at actually 811P, despite the fact it was an increased frequency, it couldn't sustain it, and eventually it just goes quiescent. And so whereas you might have that initial burst, eventually it just dies, and then you just lose transmission. So essentially you're going to affect kind of pain conduction just over time. It's just going to just die on you. So I like that one as a potential rationale for why gain of function can both be activating and inhibiting, although that's still quite controversial for the people who are actually in the field. So obviously I've given you some rationale, and so I now give you some things that we've done personally at Icagen, and actually working when we were part of Pfizer, on to overcoming the challenges of doing kind of NaV 1.9 drug discovery. One of the challenges was just to clone the channel. So that channel had not been successfully kind of expressed functionally. Despite its finding the cloning in 1999, the first time it was expressed as a stable cell line was by Al George in a background of actually an ND723, which is a mouse rat DRG hybridoma cell line, not necessarily conducive for drug discovery. We spent many years on and off trying to get it to express in either a CHO or a HEC cell, and eventually we were successful. And it turns out that you needed the beta subunits in our hands to actually get that, so we co-expressed it with beta 1, beta 2. And as you can see, we got kind of currents that look very much like the endogenous NaV 1.9, slow activating, slow inactivating. They actually have a midpoint on the IV with exactly where you'd find it in the DRG. They have this kind of inactivation-activation relationship where you get this very large window current. It's also shown that we can enhance the currents using GTP, and that doesn't seem to affect the gating, but certainly you get a lot more current, so maybe that's essentially an availability kind of effect. And the other unusual property is, if anybody's ever done NaV 1.9 in DRGs, the one thing you learn is that it seems to drift and disappear and it never comes back. And that's probably due to the fact there's actually a very slow inactivation period. So if you depolarize for very short periods, it recovers in essentially the millisecond time scale, which is probably relevant to the heart. But if you actually put on a long pulse, it essentially goes into a long-lived inactivated state that takes at least 10 minutes to recover from. So one don't know why it exists in that form, but it's there. And that makes it quite challenging to do drug discovery. This slow inactivation actually has a midpoint actually down in the sort of the minus 90, minus 100 range. And we tend to try to hold, when we're doing pharmacology, we try to produce a little bit of inactivation because classical sodium channel blockers like inactivated state. But it turns out that when we looked at local anesthetics, and here's an example of tetracaine, we didn't see very much in the way of potency difference whether we were in the resting state or the inactivated state. So that's very unusual for a sodium channel and a local anesthetic. So here we only had a threefold difference in potency, and some of this potency at minus 90 may have actually been due to rundown because it takes a long time to establish the block, and it's a tough to keep this thing from going into slow inactivated state. We did find in a compound, actually it's an Amgen compound, which is this one, which you can buy from Tocris, but it's an old NaV 1.7 inhibitor that actually is reasonably potent. It's got a 1 micromolar IC50 compared to tetracaine. and then some of these other blockers. But you'll notice that these are all very weak. And if you actually look at the same agents across 1.9 and compare them to, let's say, a reference TTX sensitive channel like 1.7 or a TTX resistant channel like 1.8, 1.9 is almost invariably less sensitive by 10 to 100 fold. There's something about 1.9 that makes this channel unusually insensitive to your classical sodium channel blockers. In fact, actually, if you look at a whole bunch of other compounds that we've tested, they all have very low potencies for classic, compounds which have been shown to block sodium channels. The odd exception, like benzocaine, which is already a weak agent, it seems to not be affected, but most of these other ones, they're shifted, like I said, 10 to 100-fold. So we've also made the mouse and the rat versions of these, because when you do drug discovery, you often found, and we have found many species differences in terms of sensitivity to sodium channels, especially when you get the selectivity you want. Again, we needed the mouse or the rat beta subunits. And obviously, it's important, since these are only 70% homologous for the human version, you just want to make sure that their pharmacology would transfer. Turns out, right now, at least for these reference compounds, they show somewhat similar sensitivities. So at least for these more classic things, again, all frame shifted relative to their other NAB counterparts, but again, no really species difference found to date. Like every other sodium channel that's been discovered, there's actually the local anesthetic binding sites there. It looks the actual sequence within the local anesthetic binding site for NAB 1.9 is almost the same as the rest of the family. When you mutate that to remove the local anesthetic binding site through these mutations, really you get nominal shift in the gating of the channels, no effects on activation, but you can see a clear change in pharmacology. So tetracaine becomes less potent. Not as much, shift is only about just under 10-fold, which is less than it would happen on 1.7, but it shifts. That compound I just showed you, which was a 1 micromole, is very sensitive to that. Essentially, we lose all activity for that compound when we make that mutation, which would suggest that it binds to the local anesthetic binding site, and the more classical benzocaine shift as well. So, we know that the local anesthetic binding site is there, and these compounds, that can't really account for why they're not sensitive to these agents. But if you actually look at the pore region as a whole, if you actually look at domain 2, S6, which is one of the lining of the pore, you'll see that just right opposite, can't see there, there's a residue, a lysine, on the domain 2, S6 that is right opposite the actual local anesthetic binding site. So if you actually look at it from a sequence point of view, it's a lysine. All other sodium channels has an asparagine there. And so obviously that's a positive charge that's sticking out into the pore. So is that a reason for the lower sensitivity? So we made a mutation where we actually replaced that lysine with the asparagine, and that didn't have much effect, if any effect, on the biophysics. So again, inactivation and activation seemed to be somewhat similar, but we found that actually tetracaine became a little bit more potent, not very much, 3-fold. Interestingly, this other TCN compound got more potent, which was weird, and whereas benzocaine was completely unaffected by that mutation. So these were small changes. Were they real? Were they biophysics? So the way to check that was to actually then put the lysine back into 1.7 and see what happened when you did that. So when we did that, you could actually look at the NAV 1.7 gating characteristics with this mutation, no difference. Basically, inactivation and activation stay the same. But when you looked at tetracaine, now when you make that mutation, the actual potency increases by 3-fold. And you look at this channel, the potency decreases by the same amount that it increased on NAV 1.9, and yet benzocaine, which was unaffected up there, was unaffected here too. So despite it being a small change, it would appear that that kind of residue is having an influence. Now, what we haven't done yet at the moment is to see if we mutate both the local anesthetic binding site and that, whether or not we can actually get a synergistic effect. But it would appear that for some molecules, they may be reaching across the pore or being sensing the positive charge on NAV 1.9. But it also then opens up the opportunity to potentially getting selective compounds, because we have actually shown at Icagen and at Pfizer, when we were part of Pfizer, that there's a residue in 1.8 that's literally in the same place on domain 3, And we were able to make very selective compounds by actually getting compounds that will interact with that residue. So it's a doable proposition. So obviously, to do drug discovery, we need a mechanism of actually being able to assay this channel. And we've used the property of where this channel, like many sodium channels, are actually activated by this pyrethroid delta methrin. This, and actually, on NaV1.9, what it does is it actually greatly slows deactivation, greatly slows closing the channel once it's open. And so what you can see in this tail current, and you can actually see it more clearly, you get this really long decay. Oh, sorry. So this channel stays open for seconds, if not minutes, after you actually open it. And therefore, you can, during that period of time, obviously you get a lot of current flow, but you also get a lot of sodium entry. And you can actually use the sodium-sensitive dyes to pick up that sodium entry based on that kind of prolonged kind of a period in which sodium can enter. Typically, it's not easy when you've only got things open for a couple of milliseconds to pick that up, but we basically showed that you could actually measure using an anti-natrium green fluorescent dye that senses sodium, a nice increased delta method-induced increase, concentration-dependent in fluorescence. So showing that we could actually pick up kind of NaV1.9 activity. We got a nice dose response curve for delta methrin. And we could exploit that to actually run a screen, which we did as part of Pfizer. I can't discuss that. Obviously, that's part of Pfizer's business. But what I can show you is that the assay worked very nicely. It was very robust. It was a 384-well assay. We could actually look, here's a response to delta methrin in the presence of the compound I showed you, TCN 1752, nice dose-related inhibition. The dose-response curve's here. It overlaps the dose-response curve we got from electrophysiology. It was a nice, robust assay. And so it allowed us to, we screened over 750,000 compounds using this assay to our dopant modulators. And so we, obviously, we've had the opportunity and still have the opportunity. We have this platform at Icagen. We can apply that. We have all of these cells available to us. And so we can find inhibitors. Now, there's an argument of, do you want inhibitors? Do you want activators? Well, actually, as part of the screen, we actually found activators too. So here's an example. Can't identify what it is, but it's here's a compound that actually caused an increase in current, but it wasn't an increase in current at every voltage. And so if you look at the properties, it's a bit like the CYP mutation. It causes a shift, a concentration-dependent shift in the voltage dependence of activation. You can see that here. No effect on inactivation. So the possibilities now, we've shown from a screening perspective, you can find inhibitors and activators, and depending on where the future takes us, I think it's a possibility to find both. So I'm going to summarize here. So rodent knockout and human genetic studies have clearly shown that NaV1.9 has a role to play in pain transmission. Obviously, now with the successful stable expression of NaV1.9 in a usable kind of cell environment, there's an opportunity by us and others to actually do serious drug discovery against this target. It provides opportunities for obviously improved characterization of this sort of elusive channel. And obviously, the goal is to kind of come up with some new drugs for the development of pain. Some challenges, the biophysical properties make it quite challenging to work with, especially the inactivation. We still don't fully understand why the pharmacology of NaV1.9 is so different from other sodium channels, but we see that as an opportunity rather than a problem. And then what is the pain modality that we should be targeting? Should we be targeting inflammatory pain that's involved in visceral pain, or other inflammatory conditions? That's something that's going to obviously evolve as this field evolves. So I just want to acknowledge actually the people who did all the work on the sort of electrophysiology, molecular biology, and characterization. They're listed here, and they're all still current employees of Icagen. Thank you.
So thanks, Dave, for a great talk. We've got time for maybe one or two questions. So I, of course, have a question for you. I've got a bunch of questions, actually. So I've heard about this gain of function and loss of function, and yet they all seem to have the same clinical feature where you have this loss of pain. So can you try and explain a little bit about that, especially with the gain of function mutants? How does that play into the sort of inability to detect pain?
Yeah, so again, it's one of this is the controversial piece in terms of is it a matter of degree that actually one of the arguments is that with gain of function you get increase of firing, but you can get fatigue.
Right.
You know, there's actually a limited increase in firing, which would be pain. It's the same way that probably if you, it's almost an adaptive process that you actually, so in the case of the gain functions that cause complete loss of pain, it's just that it's such an extreme shift that you both get fatigue or it, and I think I would argue that what's happening is you get this depolarization that then shuts down all the other sodium channels' ability to fire. But also, even if there's some background activity because of this gain of function, one of the things we're noticing is that the entry into slow inactivation, this thing that takes minutes to recover from, actually is, at least for the mutation we've looked at, actually seems to be enhanced. Okay. So whilst it appears to be gain of function, long-term actually may be a loss of function under depolarized conditions.
The 1302 mutation that
Yeah.
you had an interesting effect on the inactivation curve. It became really very shallow.
Yeah.
And also had a kink in it, I thought, at hyperpolarized potentials. Do you have an explanation?
Yeah, so
for that?
it's almost related to what I just talked about. If you look at there's a quote fast inactivation for 1.9 that occurs on the hundreds of milliseconds time scale compared to milliseconds for one sodium. There's a much slower inactivation. It takes seconds to enter. Now, with this mutation, like I said, it seems that slow inactivation starts to enter even at like minus 140. So some of that kind of shallowness on that inactivation curve might actually be the fact that we can't hold negative enough to not allow slow inactivation to accumulate.
So do you think that residue is interacting with S4, for example?
You mean the one in the lysine? No, that one sits in the pore, sticking right out into, at least from a homology model, it literally sits out, pointing into the pore opposite the local anesthetic binding site inside the channel. Yeah.
It's kind of a follow-up from Derek's question. If you were talking about designing drugs that enhance the activity, does that mean you need to go for a very high concentration of the drug? And
yes, that's the debate of whether or not you'd move through a kind of a sensitized state to I guess one of the models might be a capsaicin type. I think you might have to go through that type of. And again, I just don't know whether or not, from a treatment point, when you're at an equilibrium thing, before you even get to this sort of painful sensation, you'll have desensitized the channels anyway. Yeah. So that's one of those debates about a gain of function. Will you actually have pain before you don't have pain? Sort of.
So you'd want to put the person under general anesthetic for an hour or two first.
Again, it's the same way with the capsaicin. You often give it with a local anesthetic if you give it topically. Yeah.
Maybe I can just ask one more question, because you made it sound very, very easy, but it's been notoriously difficult to try and express these in the recombinant system.
Yeah, so it took us about 10 years.
Exactly, right. But has anybody ever tried to just biochemically characterize what the complex is in sensory neurons? Or
The person the group that's done the most work on just the protein interactions is Steve Waxman's group. They've shown that it interacts with contactin and various FGFs and stuff. And we've actually, in the early days, we tried to co-express it with all of those and see whether that would actually help, and none of them did. Ultimately, it became, I think in the end, it was is getting the actual beta subunit expression right. We have many versions of beta subunits, and not all of them express. But the ones that we and then we established, and obviously, and we know it's there because we did the same thing for mouse and rat, and so whatever that is, it works. Because it's not just a particular clonal line that we suddenly stumbled on that works. It actually, it's a strategy that seems to work